The researchers assumed it was a glitch, but then they saw the pattern. The data wasn't random noise, it was structured, it was organized, it was as if something was communicating back. The idea is that they are pulling answers from different universes simultaneously. They don't even completely understand how this is working, but the amount of power in computing is incomprehensible. Today, we're about to dive into one of the most mind-bending and transformative breakthroughs in modern science. If you thought that quantum computers were some distant possibility reserved for science fiction, think again. Quantum computing is here, and it's officially broken the rules of reality as we know it. In this video, we'll explore how quantum computers are not only revolutionizing technology but are also fundamentally reshaping our understanding of the universe. The age of quantum computing has arrived, and it's bringing with it a slew of breakthroughs that defy the conventional laws of physics. We're talking about machines that can solve complex problems in mere seconds, problems that would take traditional supercomputers thousands of years to process. But these aren't just speed bumps on the road to innovation. Quantum computers are challenging the very fabric of reality itself. Before we dive into what's going on, let's break it down. Quantum computing is based on the principles of quantum mechanics, the weird and mysterious laws that govern the behavior of particles at the smallest scales. To truly understand what's happening, we need to grasp how different quantum computing is compared to classical computing. Classical computers, the kind most of us use every day, process information using bits, those familiar ones and zeros. A bit can be either on or off, a binary state that makes up the foundation of all digital processing. However, quantum computers use qubits, quantum bits, those mysterious particles that can exist in multiple states simultaneously. This phenomenon is known as superposition. Think about it like this: imagine you have a coin, and when you flip it, it lands in two places at once, heads and tails. In quantum computing, this is essentially what a qubit can do. It can represent both 1 and 0 at the same time, increasing computational power exponentially. This is where things start to get weird because our world, the one we experience every day, is not governed by these principles. It's governed by classical physics, where objects can only exist in one state at any given time. Now, this idea of superposition allows quantum computers to perform calculations that classical computers could never hope to accomplish. But it doesn't stop there. Enter entanglement. Entanglement is another quantum phenomenon that defies logic. When two qubits become entangled, the state of one qubit directly affects the state of the other, no matter how far apart they are. It's as if two particles are connected by some mysterious force, instantly communicating with each other across space and time. This is where quantum computers really begin to break the rules of reality. In a traditional computer, if you change the state of one bit, you're affecting only that bit. But in quantum computing, a change in one qubit can instantly affect another, even if they are light years apart. But why does this matter, and why is it such a big deal? Well, quantum computing's power lies in its ability to perform massive amounts of calculations in parallel. While a classical computer processes one calculation at a time, a quantum computer can process thousands, millions, or even billions of calculations simultaneously. This creates an exponential leap in computing power, making it possible to solve incredibly complex problems in a fraction of the time. To give you a sense of the magnitude of this leap, let's talk about factorization. Factorization is the process of breaking down a number into its prime factors. For example, 15 can be factored into 3 and 5. Now imagine a large number with hundreds of digits, like a number used in modern cryptography. Classical computers would take millions of years to factor this number, making it nearly impossible to break current encryption methods. But a quantum computer, using algorithms like Schia's algorithm, can factor such a number in mere seconds. This means that quantum computers have the potential to break encryption methods that have been the foundation of cybersecurity for decades. Sensitive data, from online banking transactions to classified government communications, could be at risk. But that's not all. Quantum computers could also revolutionize fields like medicine, material science, and artificial intelligence. They could help us develop new drugs by simulating molecular structures at an unprecedented level of detail. They could help create new materials with exotic properties, opening the door to breakthroughs in energy storage, superconductivity, and more. In fact, there have already been some impressive demonstrations. In 2019, Google made headlines with their announcement of quantum supremacy. They claimed that their quantum computer, Sycamore, had completed a task that would take the world's most powerful supercomputer 10,000 years in just 200 seconds. While some scientists debated the true significance of this achievement, there's no denying that quantum computers are now capable of doing things that classical computers simply can't. However, while the potential of quantum computing is immense, we're still in the very early stages of this technology. Quantum computers are incredibly delicate, requiring extreme conditions to operate. They need to be kept at temperatures colder than outer space, and even the slightest disturbance. Quantum computers are incredibly delicate, and even the slightest disturbance can cause them to lose their quantum properties, a phenomenon known as decoherence. This makes scaling quantum computers up to a practical size a monumental challenge. Still, progress is being made. Companies like IBM, Microsoft, and Honeywell are all racing to build more powerful and stable quantum computers. In fact, just last year, researchers at the University of Chicago and Argonne National Laboratory announced they had developed a new quantum algorithm that could lead to a major breakthrough in quantum computing. This algorithm is designed to reduce errors in quantum calculations, one of the biggest challenges facing the field. So why does all of this matter? Why should we care about quantum computers breaking reality? The answer lies in the fact that quantum computers have the potential to revolutionize nearly every industry, not just in terms of speed and efficiency, but in fundamentally new ways of solving problems. Imagine being able to simulate the behavior of every molecule in a drug molecule in real time without relying on trial and error. Think about the possibilities in artificial intelligence, where quantum algorithms could allow machines to learn and adapt at an exponentially faster rate. But there's also a darker side to this quantum revolution. If quantum computers can break encryption so easily, what's stopping them from being used for malicious purposes? Cybersecurity experts are already warning that quantum hacking could become a major threat in the near future. In fact, governments and companies around the world are already working on developing quantum-resistant encryption methods to stay one step ahead of this new breed of computing. Then, there's the question of whether quantum computing will lead to a new form of artificial intelligence. We already know that AI is evolving at a rapid pace, and quantum computing could accelerate that progress to an unimaginable speed. Some theorists even speculate that quantum computers could one day give rise to a superintelligent AI, one that is capable of solving problems and making decisions that are beyond human comprehension. This raises all sorts of ethical questions. What if such an AI becomes so powerful that it exceeds human control? What if it begins to shape reality itself, manipulating the very laws of physics to suit its needs? For now, we are still in the early stages of this quantum revolution, but it's clear that quantum computers are no longer just theoretical devices. They are breaking through barriers, challenging the fundamental principles of physics, and opening up new possibilities that we can only begin to imagine. The very nature of reality itself is being rewritten, and the implications of this are still unfolding. As quantum computing advances, it will continue to push the boundaries of what's possible. Who knows what other mysteries of the universe we'll uncover as we harness this mind-boggling technology? The future is uncertain, but one thing is for sure, the quantum age is here, and reality as we know it will never be the same. In conclusion, it's official, quantum computers have broken reality. What happens next could change everything. Buckle up, because we're entering a new era, one where the laws of nature as we know them are being redefined, and the only limits are the ones we impose. The possibilities are endless, but so are the challenges. Will we rise to meet them, or will we be left behind by the very technology we've created? Only time will tell. As we continue to explore the vast potential of quantum computing, it's essential to recognize that the technology is still in its infancy. While the achievements of companies like Google, IBM, and others are groundbreaking, they are just the beginning. Quantum computers are not yet ready to solve real-world problems on a large scale, but they are getting closer, and the implications of their eventual full deployment are staggering. Let's dive deeper into the scientific and technological areas that quantum computing will influence, as well as some of the challenges that stand between us and the widespread adoption of quantum computers. First, quantum computing in medicine and healthcare. One of the most promising applications of quantum computing lies in the field of medicine. For decades, scientists have been working on trying to understand the human body at a molecular and atomic level, but due to the complexity of biological systems, progress has been slow. However, quantum computers have the potential to accelerate medical research to unprecedented levels. Imagine a scenario where a quantum computer is used to simulate every single molecule in a drug before it's even tested on humans. This is no longer science fiction. Quantum computing allows researchers to model molecules with far greater precision than is possible with classical computers. Instead of relying on expensive and time-consuming physical trials, drugs can be designed, tested, and refined within the computer itself. This could lead to the rapid development of new medications, particularly for diseases that have long been difficult to treat, such as cancer, Alzheimer's, and genetic disorders. Furthermore, quantum computing could enable the simulation of complex biological systems in real time. For instance, quantum computers could simulate the behavior of proteins, which play a central role in diseases like Parkinson's and Huntington's disease. By understanding how these proteins fold and interact, researchers could gain insights into how diseases develop and how they can be prevented or treated. Additionally, the power of quantum computing could enable personalized medicine on a scale we've never seen before. With quantum computers, doctors could potentially create models for an individual patient, simulating how different treatments would affect their body on a molecular level. This could lead to highly targeted therapies, optimizing the chances of success and minimizing side effects. Second, quantum computing in material science and engineering. Quantum computing doesn't just have applications in the biological sciences, it also promises to revolutionize material science and engineering. A quantum computer can model and simulate materials at the atomic level, something that's currently far beyond the capability of classical computers. This could lead to breakthroughs in developing new materials with properties that are impossible to achieve with today's technology. For example, quantum computing could help us discover new superconducting materials. Superconductors are materials that can conduct electricity without resistance, making them highly efficient for applications like energy transmission. However, current superconductors require extremely cold temperatures to function, making them expensive and difficult to implement on a wide scale. Quantum computers could help identify materials that can become superconductive at higher temperatures, bringing us closer to the goal of room temperature superconductivity. In the world of electronics, quantum computing could also lead to the development of faster and more efficient semiconductors. Semiconductors are the backbone of modern electronics, but the current limitations of classical computers have made it difficult to create new, faster, and more efficient designs. With quantum computing, new materials could be discovered that make electronics faster and more powerful, with applications in everything from consumer gadgets to space exploration. Quantum computing could even have a major impact on energy production and storage. One of the biggest challenges in the field of renewable energy is finding ways to store energy efficiently. Batteries, as we know them, are bulky and have limited lifespans. Quantum simulations could help design next-generation batteries that are far more efficient and durable, solving one of the biggest hurdles in renewable energy adoption. Third, quantum computing and artificial intelligence. When it comes to artificial intelligence, AI, quantum computing is poised to change the game entirely. AI systems, particularly machine learning algorithms, rely heavily on the processing power of classical computers. While traditional computers have made significant strides in AI, they still face significant limitations when it comes to processing vast amounts of data and performing complex calculations. This is where quantum computing steps in. Quantum computers can process multiple possibilities simultaneously, which could make them incredibly powerful tools for AI development. Machine learning algorithms, which require enormous computational resources to analyze data and improve models, could benefit immensely from the parallel processing power of quantum computers. One of the areas where quantum computing could have the most significant impact on AI is in optimization problems. Machine learning often involves finding the optimal solution from a large number of possible solutions. For example, when training a neural network, you must adjust its parameters to minimize error. Quantum algorithms like the Quantum Approximate Optimization Algorithm, QAOA, are already being explored to solve these types of problems more efficiently than classical computers. This could lead to faster, more accurate AI models and applications in everything from speech recognition to autonomous vehicles. Additionally, quantum computing could lead to the creation of quantum artificial intelligence, QAI, a completely new form of intelligence that is fundamentally different from classical AI. In the future, QAI could potentially solve problems that are beyond the reach of human comprehension, processing vast data sets in ways we can't even imagine. Fourth, quantum cryptography and security. With the rise of quantum computing comes an urgent need to rethink our entire approach to cybersecurity. As we mentioned earlier, quantum computers are incredibly powerful at solving problems that would take classical computers millennia to crack, particularly in the realm of cryptography. Modern encryption methods like RSA and ECC, elliptic curve cryptography, are based on mathematical problems that are difficult to solve using classical computers but are solvable in an instant with a powerful quantum computer. This has major implications for the future of cybersecurity. If quantum computers are able to break current encryption methods, sensitive data such as banking information, government secrets, and personal communications could be at risk. Hackers could use quantum computers to crack encryption systems and steal valuable information, potentially wreaking havoc on the global economy and national security. To combat this, the field of quantum cryptography has emerged. Quantum key distribution, QKD, is a method of encrypting data that uses the principles of quantum mechanics to ensure that any attempt to intercept the data will be immediately detected. With QKD, the security of the data is guaranteed by the laws of physics rather than relying on the complexity of mathematical algorithms. As quantum computers become more advanced, quantum cryptography will likely become a critical part of our cybersecurity infrastructure. However, quantum cryptography is still in the early stages of development, and we are far from a world where quantum secure communication is the norm. Researchers are currently working on creating quantum-resistant encryption algorithms that can withstand the power of future quantum computers, ensuring that our digital infrastructure remains secure in the quantum age. 5 Ethical dilemmas and potential dangers. As with any groundbreaking technology, the rise of quantum computing comes with a host of ethical dilemmas and potential dangers. One of the biggest concerns is the impact of quantum computers on privacy. If quantum computers can break existing encryption systems, then virtually all personal data could be exposed to malicious actors. Financial transactions, private messages, and medical records could all be accessed with ease, putting people's privacy and security at risk. There is also the potential for quantum computers to be weaponized. If quantum technologies are harnessed by rogue states or terrorist organizations, they could use quantum computers to break encryption systems, manipulate financial markets, or launch cyber attacks that are far beyond the capability of current technology. Governments will need to establish new protocols and international treaties to ensure that quantum computing is used responsibly and safely. On the other hand, quantum computing also raises the question of whether we are creating something that could surpass human intelligence. As quantum computers become more powerful, they will be able to process vast amounts of data and make decisions that are beyond our ability to understand. If this happens, we may face an entirely new set of ethical questions about who controls this technology and what its true purpose should be. The advent of superintelligent quantum-powered AI is a topic of growing concern. If AI systems were to gain the ability to modify their own programming and improve themselves at an exponential rate, they could quickly become uncontrollable. The very nature of intelligence itself could change, and we may find ourselves facing a world where humans no longer hold dominion over technology. 6. The future of quantum computing. So what does the future hold for quantum computing? As we've seen, this technology is still in its infancy, and we are only beginning to scratch the surface of its potential. But as quantum computers continue to advance, we can expect to see major breakthroughs in a wide variety of fields, from medicine and material science to artificial intelligence and cryptography. In the near future, we will likely see quantum computers solving increasingly complex problems, helping researchers develop new drugs, optimize supply chains, and unlock new technologies. However, quantum computers will also create new challenges, especially in the realm of cybersecurity and ethics. Governments, corporations, and researchers will need to collaborate to ensure that quantum technologies are used responsibly and that the risks associated with them are mitigated. The quantum revolution is not just about faster computers, it's about rethinking the very nature of reality itself. As we continue to push the boundaries of what's possible with quantum mechanics, we may find that our understanding of the universe and our place within it is fundamentally changed. It's official, quantum computers have broken reality, and we're standing at the dawn of a new era. The possibilities are limitless, but so are the challenges. One thing is certain, this is just the beginning.